Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Interdisciplinary and Trans-Disciplinary Studies, SOITS, Master of Arts, Environmental Studies, MAEVS. First year, MEV 14 Sustainable Natural Resource Management. Block-1 Natural Resources. Unit-4 Soil and Land Resources. 4.0 Introduction. Soil is a dynamic system which consists of highly complex system comprising of solid, liquid and gaseous phases. Soil is primarily composed of clay, humus, colloids, elemental forms of metals and non-metals, salts and organic and inorganic acids. The solid phase consists of heterogeneous mixture of organic and inorganic components. The particles in solid phase determine texture and structural properties of the soil. The organic portion consists of undecomposed organic matter and humus, whereas inorganic components are made up of minerals, salts and oxides and silicates of metals of primary and secondary origin. Water forms the liquid phase. Water is either present in free flow or adsorbed on the surface of solid particles and moves through the capillary and non-capillary voids. Gaseous phase represents air and constituent gases, e.g. CO2 and O2 occupying the empty space in the soil. The amount of water and air in the soil depends on the rainfall, irrigation and seasonal changes. 4.1 Objectives. After studying this unit, you should be able to fill circle define soil. Fill circle explain the physical, chemical and biological properties of soil. Fill circle understand the soil microbial properties and land use, and fill circle explain the soil pollution and its deleterious effects on environment. 4.2 What is soil? Definition of soil. The most widely accepted definition of soil given by Soil Science Society of America is as follows. I. The unconsolidated mineral matter on the surface of the earth that has been subjected to and shows effects of genetic and environmental factors of climate, including moisture and temperature effects, macro and microorganisms and topography, all affecting over a period of time and producing a product, that is soil. It differs from the material from which it is derived in many physical, chemical, biological and morphological properties and characteristics, e. The unconsolidated mineral material on the immediate surface of the earth, that serves as a natural medium for the growth of land plants. 4.3 Physical properties of soil. Physical properties of the soil have a significant role in providing a suitable environment and media for plant growth. The plant support, root penetration and development, drainage of water, aeration, retention of moisture and availability of plant nutrients are linked with the physical condition of the soil. The physical properties of a soil depend on the amount, size, shape, arrangement and mineral composition of its particles. These properties also depend on organic matter content and pore spaces between particles. Therefore, knowledge of physical properties of soil is important for management of lands for agriculture and other purposes. Important physical properties of soils. 1. Soil texture. 2. Soil density. 3. Porosity. 4. Soil structure. 5. Soil color. 6. Soil strength. 7. Soil air. 8. Soil temperature. 1. Soil texture. Soil particles less than 2 mm are called fine earth and are normally considered in chemical and mechanical analysis. The components of fine earth are called as sand, silt and clay based on their size. Soil texture refers to the relative proportion of these three particles or their relative percentage by weight. The proportion of each size group in a given soil, the texture, cannot be altered easily and it is considered as a basic property of a soil. Table 4.1 Soil particle size, mm. Soil particle diameter, mm. Coarse sand 2.00 minus 0.20. Fine sand 0.20 minus 0.02. Silt 0.02 minus 0.002. Clay below 0.002. Fig. 4.1 Soil texture. Look at the screen. Soil properties like moisture holding capacity, cation exchange capacity, swelling and shrinking are highest in clay, intermediate in silt and lowest in sand. Particle size bigger than 2.0 mm give rise to coarser and incoherent soil texture. Having determined the sizes of the particles, the textural classes are determined according to the triangular diagram. The major textural classes, in order of increasing fineness, are sand, loamy sands, sandy loam, loam, silt. Loam, silt, sandy clay loam, silty clay loam, sandy clay, silty clay. And clay. Sandy loams permit rapid infiltration of water, rain or irrigation, and the time of retention over the land surface is reduced. Clay loam soil have fine particles of clay and silt and are more amenable to erosion, since they have less infiltration rates and get easily dislodged, rendered into suspension and washed off. In coarse textured soils, aeration is more abundant as compared to fine textured soils. A good tilth is obtained in loam soils which are better pulverized. For seeding of crops and their root growth, sandy loams are easy to work and till, whereas clay soils offers resistance to cultivation and carrying out tillage and cultural operations. Soil texture groups, having predominance of clay particles, exhibit better chemical environment in the soil and are mainly associated with the availability of nutrients through increased cation exchange capacity, CEC. 2. Soil density. The density refers to the mass per unit volume of a substance. Soil density is expressed in two well-accepted concepts, I, bulk density, and E, particle density. A. Bulk density of soil, bulk density, BD, is defined as mass per unit volume of oven dry soil as a whole, i.e. soil particles, organic matter combined with the pore space, and is expressed in the unit of grams per cubic centimeters. Gram per cc. The lesser the pore space, the greater is the bulk density of the soil. Uncultivated and compacted soils have greater bulk density. Bulk density is lower in surface layers and becomes higher with increasing soil depth. Bulk density of compacted areas and clay soils may range from as high as 2.0 grams per cc. And in case of good forest soil having thick litter and good ground cover, it's 0.7 to 0.9 grams per cc. B. Particle density, PD, is defined as the mass per unit volume of the solid portion of oven dry soil, minerals and organic matter, and is also expressed as grams per cubic centimeters, gram per cc. Bulk density takes into consideration both the solids and pore space, while only mineral solids are considered for determining particle density. Mineral component of the soil being heavy, the particle density varies within a very narrow range of 2.60 minus 2.70 grams per cc. 3. Soil porosity. A large portion of the soil mass consists of pore spaces or voids, which are occupied either by air or water. Porosity refers to the percentage of volume in the dry soil occupied by water and air. Depending upon the size of pores, macro and micro pores are recognized. Macro pores, non-capillary, allow water and air to move rapidly. Total volume of pore space is explained and computed as per the formula given below. Since % pore space % solid space equals 100 and % pore space equals 100% solid space, % solid space equals BD, PD, x 100. Porosity % pore space equals 100 BD, PD, x 100. For example, for a soil having bulk density, BD, as 1.3 grams per cc and particle density as 2.65 grams per cc, porosity will be porosity % equals 100, 1.3, 2.65, x 100 equals 50.95%. 4. Soil structure. Soil structure refers to the arrangement of the soil particles, e.g. sand, silt and clay, and is usually manifested in different geometrical forms developed by aggregation of these particles. Such soil beds are natural, relatively permanent aggregates, separated from each other by voids or natural surfaces of weakness. Types of soil structure. A. Plate-like, platy, the horizontal dimensions are distinctly expressed and much longer than vertical dimensions, giving a flattened or compressed appearance. When the units are thick, they are called as platy, and when thin as lamina. B. Prism-like, prismatic and columnar, vertical dimensions are clearly expressed and much larger than horizontal dimensions, giving a pillar Like shape. When the top of such bud is round, the structure is called as columnar, and when flat, prismatic. C. Block-like blocky, angular and subangular blocky, horizontal and vertical dimensions of these structural units are almost equal. Angular. Blocky units are characterized by flat and sharp well-expressed corners, whereas subangular blocky units have rounded corners and faces. D. Sphere-like spheroids, aggregates in these structural units are more or less round in shape. 5. Soil porosity and permeability. Pore spaces in a soil refers to the portion of the soil volume which is not occupied by solids, either mineral or organic. Pores in soil are the result of irregular shapes of primary particles and their aggregation, the pushing forces, of penetrating roots, worms, and insects, and of expanding gases entrapped by water. Soil permeability refers to the property of the soil to allow movement of water and air and is one of the most important soil qualities. Under field conditions, all pore spaces are occupied by air and water. Sands have large and continuous pores and hence are more permeable. In contrast, clays, although containing more total pore space because of the minute size of each clay particle, have very small pores, which release water slowly. Air exchange may be inadequate for plant root growth in some wet clay soils. The best balance of water retention plus adequate air and water movement. Larger pores is in medium textured soils, such as loams. 6. Soil color. Dark soils absorb more heat than light-colored ones. Soil color indicates many soil features. A change in soil color from the adjacent soils indicates a difference in its mineral origin, parent material, or in soil development. White colors are common when salts or carbonate, lime, deposits exist in the soil. Spots of different color, mottles, usually rust-colored, indicate a soil that has periods of inadequate aeration each year. Bluish, grayish, and greenish subsoils, gleeing, with or without mottles, indicate longer periods of waterlogged conditions and inadequate aeration. Soil color determination is standardized and determined by the comparison of the soil color to Munsell color charts. Soil color notation is divided into 3 parts. Hue, the dominant spectral or rainbow color, red, yellow, blue, and green. Value, the relative blackness or whiteness, the amount of reflected light. Chroma, purity of the color, chroma number increases and the color is more brilliant as grayness decreases. 7. Soil strength. Soil strength is the degree of resistance of a soil mass to crushing or breaking. When force is applied, a non-cemented soil mass is evaluated under 2 moisture conditions, air dry and field capacity water content. When a soil mass is cemented, soil strength is evaluated when air dry and again when wet after it has soaked in water for 1 hour. 8. Soil air. To survive, all living organisms require gaseous exchanges. The most important of these in soils are for respiration by plant roots and for organic matter decomposition by microorganisms. The most desired condition is well aerated soil, a condition in which oxygen exchange between soil air and atmospheric air is rapid. The factors influencing the rate of gaseous exchange include soil pore sizes and continuity, temperature, depth in soil, wetting and drying of soil, and coverings, mulchers, on soil surface. Reduced aeration causing deficient oxygen concentrations can be caused by various factors. Some of these are 1. Waterlogging, ponding, 2. Soil compaction of loams and clays, 3. Very high contents of clay that swell when wet, thereby closing large pores, and 4. Organic matter decomposition by soil. Microorganisms that uses oxygen in soils already low in oxygen diffusion rate. ODR. 9. Soil temperature. Soil temperatures vary from perpetual frost, permafrost, at shallow depth, in many soils in frigid Alaska, to warm tropical Hawaii, where daytime temperatures of the bare soil surface seldom fall below 400 C. 1040 F. On sunny days, the standard soil temperature is measured at a depth of 50 cm, 19.5 in, or at the rock or hardpan contact if the soil is not 50 cm deep. Soil temperatures resulting from the sun's radiation change with the time of day. The maximum daily temperature at deep soil depths is delayed, even by several hours, after the time when the air temperature reaches a maximum. Conversely, on cool nights, the deep soil layers do not cool as fast as surface layers because of the insulating effect of the overlying soil. Heat flow is slower in soil than in the atmosphere. Factors influencing soil temperature. The temperature a soil attains depends on 1. How much heat reaches the soil surface, heat supply, and 2. What happens to that heat within the soil, dissipation of heat. The heat supply to the soil surface from external sources is reduced by organic soil coverings, which act as insulators. All plastic mulches make the soil hotter when the sun is shining, but transparent plastic allows greater warming than opaque plastic. A sun angle less than perpendicular to the soil surface also supplies lesser heat per unit of soil area. North-facing slopes in the northern hemisphere will receive less heat than will other directional slopes during winter months. 10. Other physical properties of soil. Additional soil physical properties include plasticity, stickiness, smeariness, and fluidity. A. Plasticity is the degree to which soil is permanently deformed, without rupture, by a force applied continuously in any direction. Plasticity is determined in the field by rolling wet soil between the hands until a 3 mm (1/8 in) cylinder is formed, with continuous rolling while it dries. This 3 mm wire will break when the soil has dried to approximately the plastic limit. B. Stickiness means the property of wet soil to adhere to another object. C. Smeariness is a field term for clays that are thixotropic. Thixotropy is the property exhibited by certain fine textured clay gels of being solid upon standing but turning liquid when shaken or mixed. Many swelling clays used in well drilling muds to lubricate the drill and lift cuttings to the surface are thixotropic. C. Fluidity refers to non-thixotropic clay soils that flow under hand pressure. 4.4 Chemical properties of soil. Soil minerals, organic matter and chemical components, soil forming processes, and climate have profound influence on the chemical nature of the soil. The seat of chemical activity in the soil is the soil colloids. Sand, silt and clay are finely ground particles of primary minerals, as against the clays with reconstituted products, secondary minerals, of the primary minerals. Properties of soil colloids. Soil colloids expose large surface area for chemical activity and bear negative electrical charge. Due to their fineness, they absorb large amount of water and remain in suspension. The negative charge on the colloidal surface attract positively charged cations e.g. Ca, Mg, Na, K, H, etc. from the soil. Solution. Under natural conditions, the natural cations and their magnitude of saturation over the soil colloids depend on the climate, soil forming processes, and parent material. Under moist temperate or subtropical high rainfall regions, the bases are leached from the surface soil, while the H ions originate from the decomposition of organic matter. Contrary to this, Na ion dominates the soil colloidal complex under semi-arid and arid conditions of tropics. Clay minerals. The three important groups of clays minerals, occurring extensively in the soil, are described as under A. Kaolinite group. This is a two-layer, 1 clay mineral in which a unit consists of alternative layers of 1 alumina, Al2, O3, and 1 silica, silicon oxide. A unit is attached to other units by means of oxygen or hydroxyl ions. A big crystal may consist of several units of this type. The units in the crystal are held in a rigid structure, having only limited interlattice space. Kaolinite group of minerals is non-expanding type, having low water holding capacity and cation exchange capacity. Because of limited space between the sheets, these minerals have low plasticity, cohesion, and swelling properties. Kaolinite has the structural formula Al4S14010O8. B. Montmorillonite group. It consists of 3 layers, 1, i.e. 2 layers of silica and 1 layer of alumina. These units are attached with O and O ions and are adequately flexible and expandable so as to permit water entry and also to expose larger surface area for the absorption of cations. It has high plasticity, cohesion, shrinking and swelling properties. As a result, these minerals can hold large amount of water and cations both on the outer surface and in the interlattice space. Under Indian conditions, this group of clay minerals is associated with black soils. The formula of montmorillonite is Al4C8020O, 4H2O. C. Illite group or hydrous micas. Illite or hydrous mica group has a similar structure as the montmorillonite, 1 sheets of alumina enclosed by 2 sheets of silicon oxide. The difference is that about 15% of silicon in silica sheet substituted by aluminum, resulting in the release of one valency which is occupied by potassium. This makes the interlattice space non-expandable. The properties of water absorption, cation exchange, cohesion and plasticity of illite are intermediate between kaolinite and illite. Ion exchange. Two kinds of ions are recognized, namely, cations and anions. Ions with positive charge are called cations e.g.h. Ca, Mg, Na, Ketc, and ions with negative charge are called anions e.g. NO3, H2, PO4, Ci, SO4, CO3, etc. Replacement or exchange of cations on the soil exchange complex, soil colloids, is called as cation exchange. Similarly, replacement or exchange of both the cations and anions in exchange reaction may be collectively designated as ion exchange. Cation exchange. The cation exchange property of soil affects the soil acidity, availability of nutrients and toxicities which in turn affect the plant growth. Any colloidal surface area that is electrically charged attracts mobile substances of opposite charge in the soil water. The dominant residual charge on most soil colloids is negative. The positively charged ions in soil water are attracted to negatively charged sites. The positively charged ions are called cations. Adsorbed cations resist removal by leaching water but can be exchanged by other cations in solution by mass action. This exchange of one positive ion by another is called cation exchange. Cation exchange takes place on the surfaces of clay and humus colloids as well as on the surfaces of plant root cell walls. The cations most numerous on exchange sites in soils are calcium, Ca2, magnesium, Mg2, hydrogen, H, sodium, Na, potassium, K, and aluminium, Al3. The proportion of these cations on the colloidal surfaces are constantly changing as ions are added from dissolving minerals or by additions of lime, gypsum, or fertilizer. The cation exchange is very important in soils because 1. The exchangeable K and Mg is a major source of plant K and Mg. 2. The amount of lime required to raise the pH of an acidic soil is greater as the CEC is greater. 3. Cation exchange sites hold Ca2, Mg2, K, Na, and NH4 ions and slow their losses by leaching. 4. Cation exchange sites hold fertilizer K and NH4 and greatly reduce their mobility in soils. 5. Cation exchange sites also act as absorbers of many metals, Cd2, Zinc2, Ne2 and Pb2, that might be present in wastewaters and prevents them from leaching to the groundwaters. The magnitude of cation exchange is measured in terms of cation exchange capacity, CEC, expressed as centimoles of cations per kilogram of soil, cmol kg1. Anion exchange. Anions such as O, NO3, SO4, PO4, take part in the anion exchange phenomenon limiting itself to organic layers or high organic matter content in the soil. Availability of phosphate and magnitude of its exchangeable form relate to the anion exchange capacity of the soil. H2, PO4, is generally exchanged with O ions. Soils rich in kaolinite mineral exhibit higher anion exchange capacity than other minerals. Soil reclamation and management, predominance of harmful cations such as sodium ions, Na, in case of alkali soils and hydrogen ions, H, in case of acid soils have deleterious effects on soil health and its fertility. Dispersion of soil aggregates due to the presence of sodium hampers aeration and entry of water into the soil which promotes runoff during rainstorms due to reduced infiltration capacity of the soil. Sodium saturation of the soil colloid complex suggests that suitable amendment should be applied to the soil so as to reduce menace of sodium toxicity. Similarly, H ions may be replaced by calcium ions by liming of acid soils. Soil physical properties: saturation of soil colloidal complex with calcium ions. Ca improves soil aggregation and thereby favorably affects the aeration and hydrophysical properties such as water transmission and its storage in the soil. The CEC and fertility of a soil can be improved by using organic matter, FYM, composts and green manuring. pH scale. Soil reaction is one of the most important characteristics of the soil which influence chemical, physical and biological environment of the soil medium. For plant growth, the pH scale is used to measure the acidity, neutrality and alkalinity. Water, H2O, is considered neutral because the concentration of H in pure water at 240 C is equal to the concentration of O ions. Therefore, pH is defined as the logarithm of the reciprocal of the H ions concentration in grams per liter. It is measured by pH scale in a suspension of soil in water. Dilution and concentration of the soil suspension affect the dissociation and thereby pH of suspension increases on dilution and decreases on concentration. It is, therefore, imperative to fix a ratio of soil to water, and it is a standard practice to use 1:2.5 soil-water ratio. The pH of soils generally ranges between 4 to 9. Importance of soil pH. Plant growth and pH. Deficiency in plant nutrients like N, P, K, Ca, Mg, and presence of soluble Fe and Ul toxic quantities adversely affect the plant growth in acid soils, pH 5.5 or less. Availability of phosphorus is reduced at low, acidic, and high, alkaline, pH. The soils with alkaline reaction, pH 7.5 and above, and the presence of O ions leads to deficiency of P, B, Fe, Cu, Mn, and zinc, which restrict the growth of the plants. Soil organisms and pH, in general, bacteria and actinomycetes function better. In soils with normal and higher pH value, the activity is markedly curtailed. When the pH drops below 5.5, fungi, however, flourish. In normal soils, fungi predominate at lower pH, but at intermediate and higher pH ranges. They meet with strong competition from bacteria and actinomycetes. Buffering capacity of the soil and its constituents offer resistance to changes in soil pH. This inherent capacity of the soil is termed as buffering capacity of the soil. The buffering action of the soil is due to influence of weak acids and salts. The colloidal complex, which is associated with a vast amount of cations, acts as an effective buffering agent. Besides, microbes decompose organic matter and produce large amounts of organic acids. Thus, due to the presence of organic acids, bases and salts, the soil pH does not change drastically upon addition of a substance of basic or acidic nature. 4.5 Biological properties of soil. Soil is vibrant with life, and a vast number of macro and micro forms of living organisms inhabit the soil and complete their life cycle in soil itself. For their requirements of energy and food, these microforms of life depend on soil, organic matter and the atmosphere. Most of the biological properties of the soil are attributed to the type and amount of organic matter. The presence of living organic substances is highly valuable for soil fertility and nutrition of crops. Organic matter and its sources. Soil, water, plants, animals and microorganisms are major components of the ecosystem. These living organisms, after completing their life cycle, die and eventually return vast quantity of organic matter to the soil. For the plants, heavy litter falls and their root systems make substantial contribution towards build-up of the organic matter in the soils. The crop residues and animal excreta are also regular sources of organic matter addition to the soil. Farmyard manure, animal dung, composts and green manures are artificial sources for replenishment of organic matter into the soil. Soil organic matter, from living or dead plant and animal residue, is a very active and important portion of the soil. It is the nitrogen reservoir, furnishes large portions of the soil phosphorus and sulfur and protects soils against erosion. It supplies the cementing substances for desirable aggregate formation, and it loosens up the soil to provide better aeration and water movement. For maximum benefit, organic matter must be readily decomposable and continuously replenished with fresh residues, roots, stem tops and manures. The soil organic matter is the most important content in the soil, even though most cultivated soils contain only 1% or more organic matter, mostly in the top 15 centimeters, 6 in, of soil. That small amount can modify a soil's physical properties and strongly affect its chemical and biological properties. Functions of organic matter. The soil organic matter as such and after decomposition, when converted to humus, performs the following vital functions in the soil. Covers the surface of the soil and is quite helpful to check soil in water losses. Organic matter lowers the evaporation of moisture from the soil surface and also brings down soil temperature during summer. Organic matter is a rich source of food for the community of macro and microorganisms in the soil. Nitrogen, phosphorus, sulfur, zinc and other micronutrients are released by the process of decomposition of the organic matter. Organic matter and many of its byproducts are slimy and sticky in nature and bind the soil particles. Water holding capacity of the soil is also increased by increasing amounts of organic matter. Organic matter maintains the soil pH within a desirable range. Undesirable rapid change in pH is prevented due to buffering attributes of the organic matter. Organic matter acts as a chelating agent and does not allow rapid use and losses of plant nutrients from the soil due to masking effect. Many of the pollutants are held and neutralized by the organic matter. Composition of organic matter. Organic matter is composed of about 45 to 50% carbon with lesser amounts of oxygen and hydrogen plus small quantities of nitrogen, phosphorus, sulfur, and many other elements. Humic substances are the colloidal, amorphous, polymeric, dark brown components of soil organic matter. Soil humus is the complex array of substances left after extensive chemical and biological breakdown of fresh plant and animal residues, which makes up 60 to 70% of the total organic carbon in soils. Main constituents of the organic matter are proteins, carbohydrates, sugars, cellulose, hemicelluloses, starches, fats, oils, waxes, lignans, pigments, hormones and minerals such as Ca, Mg, Na etc. Proteins and lignans form a major part, 80%, of the organic matter in the soilhumus complex. Active fraction of the organic matter includes materials of high mean carbon, nitrogen, C/N ratio. These components comprise of living biomass, polysaccharides etc. Passive fraction of the organic matter includes humus of the clay humus complex, humin and most of humic acids. Products of decomposition. In well-aerated soil, the end products of decomposition are CO2, NH4, NO3, H2, PO4, SO4, 2, H2O, resistant residues, and numerous other essential plant nutrient elements in smaller quantities. Nitrogen most often controls the rate of organic matter decomposition. It is needed to build proteins in new bacterial and fungal populations. The nitrogen content in the microorganisms and in organic materials is given as the carbon-nitrogen ratio. Dense populations of microorganisms inhabit the upper soil surface and have ready access to the soil nitrogen sources. Plant residues with C/N ratios of 20:1 or narrower have sufficient nitrogen to supply the decomposing microorganisms and also to release nitrogen for plant use. Benefits of soil organic matter. 1. Organic matter is the source of 90 to 95% of the nitrogen in unfertilized soils. 2. Organic matter can be the major source of both available phosphorus and available sulfur. 3. Organic matter contributes to the carbon cycle and is 30 to 70% of the total amount. 4. Organic matter commonly increases water holding capacity of the soil. It increases available water content even in sandy soils. 5. Organic matter acts as a chelate. 6. Organic matter is a source of carbon supply for many microorganisms that perform other beneficial functions in soil. 7. Organic matter reduces erosion and shades the soil. It keeps the soil cooler in very hot weather and warmer in winter. Carbon cycle. Carbon is one of the most dynamic elements of natural ecosystem. It follows a pathway called carbon cycle, which shows its immobilization in organic form. From the atmosphere, this immobilized carbon is released back to atmosphere when mineralized by the microorganisms in the form of carbon dioxide. The process of photosynthesis effectively converts vast quantities of CO2 to plant food, sugars, starches etc. and locks up carbon in plant bodies. The breakdown of the locked carbon in organic compounds is carried out by the activity of microorganisms, organisms and their residues. In the soil there are many types of organisms which are both beneficial and harmful to soil and plants, but the beneficial ones exceed them in effect. The soil, organic matter, macroorganisms and microorganisms are all important for soil health, but fungi and bacteria are the most important soil organic carbon creators and organic matter decomposers. A symbiotic relationship is that in which two different organisms live in association, with both benefiting from each other. The most lively symbiotic root-fungi association is found most dramatically on roots of trees through a microorganism called as mycorrhizae, though now its symbiotic association is evident with most plants. Mycorrhiza increase the root volume and hence aid in nutrient and water uptake. The bacterium Rhizobia, N2. Fixing bacteria, form small pinkish nodules on the roots of legumes which aid in nitrogen fixation in the leguminous plants. Similar microbe-plant relationships exist on many other plants, even on corn and other grasses. Certain bacteria, called autotrophs, get their energy by oxidizing important soil elements which include nitrogen, sulfur, iron, manganese, and carbon monoxide. Other microorganisms, like some algae, fixes atmospheric nitrogen and become part of the organic matter. Actinomycetes fix nitrogen and help in decomposition of organic materials. Protozoa are also the composers and act as predators on bacteria. Microorganisms decompose organic materials. Enzymes are produced by the decomposer and are directly responsible for the decomposition. Enzymes reduce the activation energy necessary to break the bonds of the organic materials. Numerous enzymes are needed for decomposition of the complex variety of organic substances. The amount of available nitrogen in the soil greatly affects the rate of decomposition. Residues with carbon-nitrogen ratios wider than about 30, one will lack adequate nitrogen for optimum decomposition rates. Other factors that promote optimum organic matter decomposition are near neutral soil pH, moist soil, temperatures about 29 to 350 C, and adequate levels of all nutrients. After the active decomposition has taken place, organic matter residues are collectively called humus. Organic matter, humus, is constantly undergoing change and must be replenished continuously to maintain soil productivity. The sources already mentioned can be supplemented by bringing in organic amendments, such as animal manures, municipal sewage sludge and logging and wood manufacturing refuse, industrial organic residues, and food processing residues. Of the total residues produced, crop residues comprise about 70% and animal manures about 23%. 4.6 Soil microbial properties. Soil microflora and fauna. Living components in the soil consist of plant roots and various forms of flora and fauna. Earthworms, termites, ants and microorganisms such as fungi, algae, bacteria, actinomycetes along with microanimal life e.g. protozoa and nematodes are quite in abundance. Other macroforms including arthropods, mammals and snails also inhabit the soil. It is estimated that in 1 gram of soil, the number of bacteria is more than a billion, actinomycetes about 10 million, fungi 1 million and algae about 1 lakh. Classification of soil organisms. The most expansive system has 5 kingdoms: Animalia, Plantae, Fungi, Protista, and Monera. Bacteria and fungi are of particular interest in the study of soils because they do most of the organic matter decomposition, fix nitrogen. oxidize or reduce elements, and include most of the disease-causing organisms. Animalia, rodents, worms and insects. Large burrowing animals aerate the soil and alter its fertility and structure. Earthworms ingest organic matter and fine-textured soil are excreted as small granular aggregates. Earthworms aerate and stir the soil, which allows better water infiltration and easier root penetration. Arthropods feed mostly on decaying vegetation and help to aerate the soil with their burrows. Algae. Soil algae are microscopic organisms that carry on photosynthesis and now reclassified into cyanobacteria, also called blue-green bacteria. In soils kept moist and fertile, algal growth can produce considerable amounts of organic material. Fungi. Fungi are vigorous decomposers of organic matter and readily attack cellulose, woody materials, lignans, gums, and other complex compounds, even in quite acidic conditions. Fungi also secrete substances that aid in the formation of water-stable soil aggregates. Mycorrhizae. Mycorrhizae form mutually beneficial, symbiotic relationships with plant roots. The plant roots transmit substances to the fungi and the fungi aid in transmitting nutrients and water to the plant roots. The fungal hyphae may extend the roots lengths 100 times. Soil bacteria. Bacteria are classified by nutritional patterns. Autotrophic, self-nutritive. Bacteria manufacture their food by the synthesis of inorganic materials, as plants do in photosynthesis. Heterotrophic bacteria derive their food, carbon, and energy directly from organic substances. Fungi, protozoa, animals and most bacteria are heterotrophs. Autotrophic bacteria obtain their nutritive carbon from carbon dioxide, and specific groups can oxidize ammonium, nitrites, sulfides, sulfur, ferrous iron, manganese ions, hydrogen gas, and carbon monoxide. The oxidation transforms nitrites, sulfides, and carbon monoxide to useful nitrates, sulfates, and carbon dioxide. Heterotrophic bacteria are those that depend upon organic matter for their nutrition, and most soil bacteria are in this group. Heterotrophic bacteria include both nitrogen-fixing and non-nitrogen-fixing groups. The nitrogen-fixing bacteria are further subdivided into symbiotic and non-symbiotic bacteria. Heterotrophic bacteria that do not fix nitrogen are the most prevalent soil bacteria and account for much of the decomposition of organic materials. Symbiotic bacteria, the heterotrophic bacteria that fix atmospheric dinitrogen gas in plant root nodules. Symbiotic bacteria have a mutually helpful relationship with their host plants. The best-known symbiotic bacteria belong to the genus Rhizobium. Non-symbiotic and two fixing heterotrophic bacteria, they live free from any association with another organism. The anaerobic Clostridium is usually more abundant in soils than the aerobic Azotobacter. Actinomycetes. Actinomycetes are taxonomically and morphologically related to both fungi and bacteria but are usually classified with bacteria. Actinomycetes aid in decomposition of organic matter, especially cellulose and other resistant organic molecules. Hence, actinomycetes aid in the development of water-stable soil structure. Definite actinomycete plant symbiosis has been established for many plants. Actinomycetes infect at least 7 different botanical families, whereas Rhizobia bacteria infect only the family Leguminosae. Soil and land use parameters. Land evaluation for land use planning can be done for rural, agricultural purposes, and urban areas both. The effect of land use on 1. Quality of the environment and 2. Environmental sustainability of agricultural production are major issues. The problems of concern include pollution with nitrate, phosphate and biocides, erosion of land, declining soil fertility, low input farming etc. Soil and land use problems may have agronomic, economic and social dimensions. This evaluation involves creation of land capability classes, subclasses and more studies like soil and water conservation practices. It thus helps the farmers in planning out the agricultural operations that can be carried out in their farmlands. Table 4.3 Land capability classes, their characteristics and recommended land uses. Classes characteristics and recommended land uses. These are deep productive soils easily worked on nearly level land. Not subject to overland flow, no or slight risk of damage when cultivated. Use of fertilizer and lime, cover crops and crop rotation are required to maintain soil fertility and soil structure. 2. These are productive soils on gentle slopes, moderate depth, subject to occasional overland flow, may require drainage, moderate risk of damage when cultivated. Use crop rotations, water control systems, or special tillage practices to control erosion. 3. Soils are of moderate fertility on moderately steep slopes subject to severe erosion and severe risk of damage but can be used for crops, provided adequate plant cover is maintained. Hay or other sod crops should be grown instead of row crops. IV. These are good soils on steep slopes, subject to severe erosion, with severe risk of damage but may be cultivated occasionally if handled with great care. Keep in hay or pasture but a grain crop may be grown once in 5 or 6 years. Land is too wet or stony which make it unsuitable for cultivation of crops, subject to only slight erosion if properly managed, should be used for pasture of forestry but grazing should be regulated to prevent cover from being destroyed. These are shallow soils on steep slopes, used for grazing and forestry. Grazing should be regulated to preserve plant cover. If the plant cover is destroyed, use should be restricted until cover is re-established. 7. These are steep, rough, eroded lands with shallow soils, also includes drought and swampy land, severe risk of damage even when used for pasture or forestry. Strict grazing or forest management must be applied. 8. Very rough land, not suitable even for woodland or grazing, reserved for wildlife, recreation or watershed consideration. 4.7. Soil pollution. Soils are nature's disposal, its sewage treatment plant, its water purifier, and at times, also a pollutant. Soils are valuable as cleansers of the earth's environments. The soil is a physical filter, sieving action, a chemical filter, adsorption and precipitation, and a biological filter, decomposition of organic materials, as well as the receptacle for all things buried and disposed of beneath and on the surface. Many toxins added to soils can build up to concentrations that become serious threats to plant and animal health. The best management practices, BMPs, are being devised for all imaginable activities that might contribute to pollution of soil and water. 1. BMPs for application of nitrogen fertilizer to crops. A. Application shall be limited to the amount necessary to meet projected crop needs, eliminates freedom to add extra fertilizer, requires knowledge of crop and soil needs. B. Applications shall be timed to be as efficient as possible. C. Method of addition shall be to root zone to the area of maximum uptake. D. Irrigation shall be managed to minimize nitrogen loss by leaching and runoff. A. Tillage practices that maximize soil binding and nitrogen uptake shall be used. Nitrogen and phosphorus, which are added in agricultural operations, are the major nutrients of concern in pollution. Table 4.6. Some of the potentially adverse environmental and health effects caused by forms of nitrogen. Effect causative agent. Environmental quality, eutrophication, corrosive damage, nitrogen sources in surface waters, hydrogen nitrate in rainfall, acid rain, ozone layer depletion, human health, methemoglobinemia in infants and elderly, also livestock, respiratory illness, cancer, nitrous oxides from fuels, denitrification, and industrial stack emissions, excess NO3 and NO2, in water and food, pans and other nitrogen oxides, nitrosamines from NO2, and secondary amines in food, fertilizer increase algal growth in surface waters and mosquitoes in shallow water, in which they are washed. Eutrophication is defined as increased water fertility, which causes accelerated algae and water plant growth. Often, phosphorus, which is usually scarce in water because it has low solubility, is the major cause of eutrophication, but nitrogen and other nutrients also contribute to the problem. The usual ways phosphate enters waters are 1. From municipal sewage with its high phosphate detergents, 2. From certain industrial wastes, and 3. Piggyback is phosphate adsorbed onto soil particles eroded into waters. Nitrogen in groundwater. Nearly all nitrogen fertilizer, except organic and other slow-release fertilizer, are very soluble in water, and the final oxidized form, nitrate, moves readily in the water. Heavy rain and irrigation following nitrogen application can wash the fertilizer off the soil with surface flow and carry urea and nitrates deep into the drainage waters. Sandy soil are particularly susceptible to this. Nitrogen also comes from decomposing organic matter. In a study, it was also found that approximately 37% of the total soluble nitrogen comes from soil. Humus, 22% from human and animal manures, 18% originally from fixation by soil bacteria and algae, and 9% from rainfall. Only 13% comes from fertilizer added to soils. The most important factors that influence the amount of nitrate movement to groundwater or surface waters are: 1. The amount of nitrate dissolved in the soil solution. 2. The rate of its use by plant. 3. The rate of immobilization into soil microorganisms or newly synthesized soil organic matter. 4. The amount of water available for runoff and leaching through the soil. And 5. Soil permeability. Soil heavily fertilized above levels recommended by BMPs and soils naturally high in fertility are potential sources of nitrate contamination in groundwater or runoff waters. Methods that can help to minimize nitrate pollution. 1. Nitrification inhibitors, such as neem-coated urea and N-Serve, that retard oxidation of NH4 to NO3, can be applied. 2. Organic and other slow-release or slowly soluble fertilizer, where they are suitable, can be added at appropriate rates. 3. Applications of predetermined minimum amounts of fertilizer can be carefully timed. Split applications. Methemoglobinemia. Nitrate becomes toxic to any animal with a disrupted digestive tract in which the conditions cause microbes to reduce nitrate ion to nitrite ion in large amounts. This effect is called methemoglobinemia. The nitrite is absorbed into the bloodstream, where it oxidizes oxyhemoglobin, the oxygen carrier, to methemoglobin, which cannot carry oxygen. The young mammal suffocates. The blue coloring, blue baby, is called cyanosis. Pesticide. Pests are any noxious, destructive, or troublesome organisms. Pesticide are chemicals to kill pest organisms. DDT, a magic substance. The story of DDT is a classic example of a magic substance capable of unbelievably good pest control. Eventually, it was also shown to be a problem. DDT was developed by a chemist in the 1880s, but not as a pesticide. In 1939, Paul Muller tried it as a pesticide. DDT is still an excellent insecticide, but it has two major disadvantages. 1. Its half-life in the environment is too long, 10 to 25 years, and 2. It is bioaccumulated in the fat of animals. What criteria define a good pesticide? 1. The pesticide must be short-lived in the environment. It must not exist long enough to bioaccumulate and biomagnify in the food chains. 2. The pesticide must not be carcinogenic, teratogenic, or cause mutation. 3. The pesticide must be effective yet able to be safely handled. Extent of pesticidal pollution. Agriculture accounts for more than 50% of all pesticide used in the world, although less than 5% of pesticide added are lost into groundwater. The desired limit is zero contamination. Groundwater and soil pollution is probably the major environmental problem facing agriculture in this century. With over half of the people in the world using groundwater for drinking, this statement may well be accurate. Despite the increased effort to reduce pollution, greater effort would be expended toward developing suitable cultural and biological methods of pest control, which would be helpful in self-sustaining agriculture and pesticide-free soil. There are alternatives, or perhaps more correctly termed, partial substitutes to the use of these chemical pesticide. The use of natural predators, biological control, is increasing. The cottony cushion scale insect, which devastated citrus trees, is controlled by two Australian insects, a small parasite fly and a predatory ladybird beetle. Another pest, the sugarcane leaf hopper, threatened To devastate the Hawaiian sugarcane industry, a total of 5 insects parasitizing the leafhopper eggs finally brought the problem under control. Other control techniques involve disease-causing bacteria that kill certain pest larvae and larvae that feed on certain weeds, thus partially controlling the larvae. Cultural control is the control of pests by management and physical activities. Other ways to reduce pesticide uses include 1. Breeding disease-resistant plant varieties, 2. Male sterilization by irradiation, and 3. Some use of natural chemicals. One example of natural chemicals is the use of juvenile hormones, which keep the larval stage from becoming an adult. Sex attractants included, as pheromones, have been used to 1. Attract insects to traps and 2. Confuse males so that they cannot find mates, thus reducing viable eggs. Wastewaters added to soils. Wastewaters include domestic sewage effluents as well as an almost unlimited variety of liquid industrial wastes. Soluble salts and organic chemicals may continue to flow with the water to groundwater or surface waters. In general, the disposal of wastewaters on land or into waters is permitted only if it does not cause 1. Extensive groundwater pollution, 2. A direct public health hazard, 3. An accumulation in the soil or water of hazardous substances that can get into the food chain, 4. An accumulation of pollutants such as odors into the atmosphere, and 5. Other aesthetic losses within limits. Solid wastes applied to soils. Solid wastes are animal manures, sewage sludges, food processing wastes, municipal leaf and garbage composts, and many other residues. These materials are being added in increasing amounts to soils. To what extent do these wastes added to soils pose environmental pollution problems? Sewage sludges. For centuries people in Asian continent have recycled human waste through the soil to utilize the nutrients and organic materials it contains. In Western developed countries such use has not been popular, largely due to concern about spreading human diseases and the aesthetics of the practice. Animal manures are beneficial to crops. Human wastes could be and could not be as useful. Crop trash. Restrictions on crop trash burning, which have been recommended to reduce air pollution, seriously concern paddy and sugarcane growers, who customarily burn tons of residual leaf in the field before and after harvest. Such burning reduces weeds, reduces insect pests, and helps clear the field for harvesting. Soluble salts. All natural waters contain dissolved mineral substances called soluble salts. These soluble salts cause many problems like alkaline soils, sodic soils, and saline soils. These soils require best management practices for crop cultivation. Damages from soluble salts. Salt pollution from agricultural runoff water is largely non-point pollution, which means the pollution does not always derive from one source, or point, but from a combination of sources, for example, lateral seepage flow and salt carried from the fields in irrigation wastewater. Soil sediments. Eroded soil becomes a serious pollutant, both as a physical problem and because of chemicals it carries adsorbed to the particles' surfaces. The control of soil erosion will be beneficial to solving several pollution problems. 4.8 Summary. Through this unit, we have discussed physical, chemical and biological properties of soil and soil pollution. Thank you for watching. We will see you in the next video, with next chapter.